Hello everyone, welcome back on another video on digital signal processor. In the last two videos we have seen the analog to digital conversions and we have understood the basic principle behind analog to digital converters for C2000 microcontrollers, especially Launchpad. And we have seen the how to configure analog to digital converter and different modules, different channels, different SOCs. And we have seen the how to use the register set to configure the analog to digital converters. In this video we are going to learn about the practical implementation of single channel single SOC using Code Composer Studio. So let's begin with the video. So here we have created a project in a Code Composer Studio and we have created the C file, that is ADC_continuous.c file, and in the C file we have make necessary functions for analog to digital converters. So to configure the analog to digital converter, we have to set the channel, its channel triggering sources and start of the conversions and so on. So these are the different registers set, and the register set will be configured the analog to digital converter module. So the first register in this category comes under the ADC control register 1, where ADC control register 1 will define the input pulse position, interrupt pulse generation control register, ADC power down mode and ADC BG channel, whereas ADC control register 2 will defining the prescaler, resolution and signal mode. Now if we are looking at the configure ADC functions, and these functions we have created to configure the analog to digital converter, and we are configuring the ADC A module. You can see that we have configured the ADC A module, and these registers we have written in EAllow and EDisable, because the ADC registers are the protected set of registers, and to access these registers we have to allow the path, and once we have accessed the registers we have to disable this path. So once we have enabled, we have used the EAllow and EDisable, and to configure the analog to digital converter we have set the ADC clock by 4. So by writing the ADC control register 2.bit.prescale equals to 6, that means we are dividing the ADC clock, we are dividing the system clock by 4 to achieve the ADC clock. So we are having the system clock is 200 megahertz, and the frequency is divided by 4, so we are getting the ADC clock is 50 megahertz. So now next is we have to set the resolution and the mode of operations. So the resolutions, either it will be 12-bit and it could be a 16-bit resolution, and mode could be single-ended and differential. So to configure the resolutions we have to write the ADC set mode, and in this field we have to write, this field is for the resolution and this field is for mode. So we have used the mode as a single-ended. So to use a single-ended we have to write a 0, and to configure the analog to digital converter as a differential we have to write it as 1. Further, if you are looking at the resolutions, if we are using the 12-bit resolutions, we have to write the speed as 0, and if we are writing the resolution is 16-bit, that means we have to write the speed as 1. So we are using, in this project, we are using the resolution is 12-bit resolution and the mode is single-ended. Therefore, we have considered the resolution and the mode is 00. And to set the ADCA, we have configured the ADC underscore ADCA. That means it configured the HA module. So now, if you are looking at the interrupt pulse position, and that positions we have set to 1, that means set pulse position to left. And once we have set the pulse position, now we have to power up the analog to digital converter. So to power up the analog to digital converter, we have written the ADCA register ADC control 1.bit.adc pwtnz. That means power down mode is equals to 1. That means we have powered up the analog to digital converters. And the delay is provided after these lines because the analog to digital converter will take some time to power up. Therefore, we have provided the 1000 microsecond time, that is 1 milliseconds time, to power up the analog to digital converter. Next, once we have defining the resolutions and mode, and we have powered up the analog to digital converter, now we have to configure the ADC for particular channel. So here we have used the SOC0 control register .bit.channel selections bit, and the channel selections bit will be equals to 1, and the 1 will be configured the ADC IN-A1 channel. If you are writing here 2, it will be configuring the ADC A2 channel. And the prescaler bit we have considered as 19. Further, the trigger selections field for the SOC0 control register, and that we have considered as 1 because we are triggering the analog to digital converter with CPU 1 timer 0. So if you are looking in this slide that the trigger selections field here, and we have considered the trigger selection is 01, that means we have considered the trigger selection from the CPU timer 0, and we are having the different options to trigger the analog to digital converter, that is the EPWM, external SOC, and CPU 1 timers and CPU 2 timers, because the analog to digital converter we can configure in both the CPUs because it is a dual core processor. And for the channel selections, we have considered the single-ended analog to digital converter. So we have considered the 1 in this field, we have written as 1. That means we have selected the ADC IN-A0, the ADC IN-A1 to configure the analog to digital converter, and the acquisition prescaler we have considered as a 19 based upon the sampling window. Now, once we have selected the channels, its window, now we have to configure the interrupt mode. So to configure the interrupt mode, at what time we have to generate an interrupt, ADC should generate the interrupt. So for that one, we have to select the interrupt selection register. So to select interrupt selection register, this field we have to, in this field we have to select the interrupt positions. So here we are using the SOC0, therefore after end of the conversion 0, the interrupt should generate. So here in this field we are writing a 00, and for INT1 SEL we are writing a 0, and the interrupt enable, and in this field we are enabling the interrupt, and interrupt 1 count we are using a 1 shot pulse generated until flag is cleared by the user. So here we are using 0. So by default this value will be 0. So now we will be looking in the code what to write in the code. So you can see that the ADC register A So ADC register A, ADC interrupt selections 1 and 2 dot bit dot interrupt 1 selection that equals to 0. That means for the SOC 0, end of the conversions 0 will be generate the interrupt 1. And once we have selected the EOC 0, at the end of the conversion 0 interrupt is generated, and we have enabling the interrupt 1 by making equals to 1. Further, whenever the interrupt is generated, the interrupt flag is cleared. So to clear the interrupt flag, we are using the interrupt flag clear dot bit dot ADC interrupt 1 equals to 1. That makes sure that interrupt 1 flag is cleared. So this is the basic configurations for the single channel analog to digital converter for the launch pad. Now once interrupt is generated, it should goes to its ISR. So in the ISR we have to clear its overflow flag and interrupt flag register. So we will go to the ISR and we will look at what we have written in the ISR. So whenever the interrupt is generated, whenever end of the conversion is done, it will comes to ADC ISR, and in the ADC ISR we have used the SOC 0, so the results will be stored in result 0. So you can see that ADC A, because we are using A module, result registers dot ADC results 0, and the results we have stored in ADC result register. So our 12-bit mode for the analog to digital converter 12-bit mode, we are getting maximum of 4095 values, that is corresponding to 3 volt. So 1 volt will be corresponding to 3 divided by 4095. So the whatever voltage we are giving, the voltage read will be this ADC results multiplied by 3 divided by 4095. So once we have stored the register in the voltage read value, now we have to clear the interrupt flag. So to clear the interrupt flag, we are considering the ADC interrupt flag clear dot bit dot ADC interrupt equals to 1. That will make sure that interrupt flag 1 is cleared. So further we will check if any overflow flag occurs or not. If any overflow flag is occurred, we are checking if any overflow flag is occurred, that equals to 1. Again we are clearing the overflow flag as well as interrupt flag. So once we have cleared the flag registers, we have acknowledged the pi group 1 for the analog to digital converter. So it will allow us for the next interrupt for analog to digital converter. Now we have written the its interrupt. Now we have to call these functions in the main function. So to call the main functions, we have to go to the main. So these are the two functions which we have written, that is a void configure ADC void, and for the interrupt we have written interrupt void ADC ISR. Now we will go to the main function. In the main function we have configured the ADC, and this ADC functions we have called, and this function will configure the analog to digital converter A module for the single channel single-ended 12-bit resolution. Okay, so next we have to call the interrupt initializations. This is the interrupt init module, interrupt vector table, and interrupt by control register, and interrupt by vector table. Now for the ADC ISR, we have to call the pi vector table dot ADC A1 underscore INT equals to address of ADC ISR. So whenever the interrupt is coming from the ADC interrupt, it will go to the ADC ISR, and in the ADC ISR, whatever functioning is there, whatever flag register is there, it will clear that flag register, and it will acknowledge the pi group register, and it will come back to the its main loop. So here we have used the CPU timer. For every 1 second, the analog to digital converter will be triggered to start of the conversions. So once this is done, we have to enable the pi group 1.1 for the ADC A module, and the remaining thing will be the same as we have configured the LCD and LCD code. If you want to looking how the LCD is configured, you can check the link in the descriptions for the video shown here. So now we will run this. So it is showing the no errors. Now we will build this project. It will take some time to building this project. Now we will run this, and we will see the main program. So here you can see that we are having the launchpad, and we have configured the DAC channel B. So DAC channel B output is this one, and the ADC channel 1 is this one, and we are changing the DAC output by the rotary encoder, and the rotary encoder is given here, and the value of the rotary encoder is displayed on the display on this LCD display. So now what we will do, we will run the display, and we will see that you can see that the voltage is changing. If we are changing the voltage from here, so you can see that this ADC results and the voltage read is also changing. It is 0.6, 0.8, it is 1.3, 1.4. You can see that the value is the value set from the encoder, and the voltage read is reading from the analog to digital converter. So you can see that the value is changing for the analog to digital converter. So this is the value which is changing, and this is the value which we are giving from the encoder, and this is giving to the DAC B, and this is the voltage which is reading from ADC in A0. So this is the way you can implement the analog to digital converter for single channel, and in the multiple module we will look at in the next video of the analog to digital converter series. And if you want me to make such kind of video, comment me in the comment section, and don't forget to like, share and subscribe the channel. Thank you. See you in the next video.